So I'm going to give you a brief overview of what we've managed to do so far with the ACTS for Atlas. So you can go to the next slide. So the Atlas software framework is called Athena, and it manages most of the Atlas production workflow from simulation to reconstruction. And what we've done so far is integrate the ACTS as an external module to replace progressively some aspect of the reconstruction. So for that, we've created different interfaces that allows us to use some of the ACTS tools with the Atlas detector in Athena. So if you have a GitLab link here that shows you the different interfaces that have been implemented so far. So for now, what we have access to mostly is conversion of the geometry from the Athena one to the ACTS one, material mapping for surfaces and volume, propagation through the geometry, and vertexing. So I'm saying available now, and it also includes some stuff that are in development and will be available soon. So you can go to the next slide. So the first thing that was important to put into place is a way to convert from the geometry as it is stored in Athena to the way it's stored in the ACTS so that we can use it there. So what we've achieved is to take the Atlas detector elements, which are stored in Athena in the detector manager, and convert those Atlas detector elements into ACTS1. Those can then be used to create layer and volume builder, and thus build an ACTS geometry. And so that's what we've done for the Atlas inner detector. Similarly, you can do the same for the Atlas event context that can be converted into an ACTS1 for alignment purpose, event per event. So this we've done, so as I said, for the inner detector, for the pixel, the SCT, and the TRT. And if you look on the bottom right, what you can see here is all the different line constraint surfaces for the implementation of the pixel plus SCT that was used for material mapping test. So you can go to the next slide. So with this geometry translated to the ACTS geometry, you can do a couple of things. You can extract 3D object for visualization. So that's what you can see here on the bottom left. So you can extract this geometry as .obj files, and then so here we do a rendering using Blender that allows us to have this beautiful Atlas inner detector 3D model. You can also, with this geometry, extract the geometry as a JSON file that can be used to perform some initialization of the material mapping that I'm going to present you just after. So the idea is that you extract a file similar to what you can have on the bottom right here that gives you the name of the different detectors, the different sublayers, etc., etc. And what you can do, for example, with those JSON files is really easily edit them. For example, to change what kind of binning you would use in the material mapping, or which kind of surfaces you want to map your material onto. So that's here you have different variables that are pointed with arrows, and those are what the kind of variable that you could edit directly into the JSON file. So if you go to the next slide, I show the material mapping. Thank you. So once you
took a bit.
Is there a problem?
No, it took a bit. It's all good. Go ahead.
Okay. So once we have extracted our geometry, the next step is to decorate the geometry with material. So to do that, what you need to do is do using Gen4 a Gentino scan of your detector, so the Atlas detector in that case. And what this Gentino scan is going to do is propagate through your detector and create it when it interacts with material, giving you specific information about the material at any given point. So that's what you can see on the bottom right here. So for the Atlas inner detector, so you can see the different shapes that we already saw in the geometry before. And once you have all those material information, you can use the ACTS surface material mapping to associate the material onto the different surfaces. So this is done by taking the track associated to one of those Gentino particles, taking a heat which corresponds to a specific material and associating it to the surface crossed by the track, which is the closest. And this is done using ACTS. So by default, we have a default binning that is implemented when we create the geometry, but this can be completely optimized and changed by hand using the JSON file that I presented on the previous slide. So once you've done this mapping, the map can be also stored as a JSON file that can then be used later to decorate the tracking geometry. So for now, I've done it for the pixel and the SCT. And for the TRT and the calorimeter, we are planning to use volume-based volume mapping instead of using a surface mapping. I will talk a bit more on that later. So you can go to the next slide. So to validate this material mapping, we can use the extrapolation tool that has from the ACTS that has been implemented in Athena. So since you have these interfaces, you can directly use the Atlas geometry and the Atlas magnetic field. And the way we are going to use this for validation is that we are going to compare the amount of material crossed by one of the Gentino tracks that we have obtained at the beginning with the amount of material crossed by a propagation through the detector. So you can do this as a function of either eta or phi, so that's the two bottom plots that you can see here. So the black point represents the amount of material in terms of x0 crossed by the propagation propagating through the geometry decorated with the material map. And the red point is the amount of material for the Gentino scan. And you see that we have already a quite good agreement. So it's less than 10% between the two as function of eta and as function of phi. And this map is absolutely not optimized yet. The binning has not been changed. We don't have enough statistics. And this was done during the weekend. So this is already what we can do without too much work into it. And we could probably achieve much more better result by optimizing it a little bit. So you can go to the next slide. So what I just showed you was for the pixels and the strip. The last part of the Atlas inner detector is a TRT. And it's a bit of a different environment compared to the two previous detectors, in the sense that since it's packed with gas and it's quite dense in material, the approach of the surface-based approach is not necessarily the best one. So we are currently thinking about how we want to work with this detector, how we want to describe it, and how we want to do our extrapolation. So the current Atlas approach is to implement it in the same fashion as the rest of the inner detector. So all the TRT materials that you can see here on the top left as those big black squares, those materials are mapped onto different surfaces, like for the pixel and the SCT. And you do then a stepwise track extrapolation that goes through vacuum, and then a pointwise material interaction at each step when you find a new surfaces. For our ACTS approach, we are thinking about using a volume-based approach. So you would have a 3D grid that would contain your material, and then you could use a stepwise extrapolation through matter instead of through a vacuum with a continuous material interaction along the steps. So which would be the same approach as what you would do using a calorimeter. So that's something we are working on right now. If you go to the next slide. So the last big thing we've implemented in Athena is the vertexing. So the ACTS primary vertexing has been integrated into Athena. So you have interfaces and tool so that it's available there. What we need to do is a conversion between the Athena EDM and the ACTS EDM and vice versa, so that those algorithms can, those tools can be integrated into Atlas algorithm directly using the ACTS approach. So the validation of the ACTS adaptive multi-vertex finder is ongoing. So we are comparing it to the Athena implementation. So for that, we are doing different performance studies using different validation. So on the right here, you can see two validation plots. So comparing the result for the ACTS and Athena. So on the top, you have the position of the reconstructed vertex. So you see that those are extremely close. And on the bottom, you have the number of reconstructed vertex, and you see that it's 0. So it's the performance are extremely similar in terms of reconstruction performance, while being faster. So the plan is to fully validate the ACTS vertexing and then to switch from the Athena one to the ACTS one. So you can go to the next slide. So the last thing we've been working on recently is the creation of some kind of nicely Athena build with the latest version of the ACTS, because of one of our biggest constraints when we have been trying to integrate the ACTS into Athena, that it can sometimes take a bit of time to have access to the latest core development in the Athena master. So to go around this problem, we decided that we will build in an IT fashion a build of Athena with the latest version of the ACTS. So here you have, if you're interested, a wiki page that explains you how you can build Athena with the latest ACTS release, but it takes quite a bit of space to do so. And our plan is to use GitLab CI Runner to build, so every night, a nightly build. So this is done in 3 steps. First, we set up the Atlas environment, clone Athena, clone the Atlas external. In the Atlas external, we would update the ACTS version to the latest one, and then do the build of the external and the build of Athena, and install everything on EOS so that we can easily have access to it. So we've looked a little bit into that. We think we can store at least a week worth of build on EOS. And if then someone wants to work on an ACTS implementation, the only thing they have to do is to build against this install. So usually building this ACTS directory in which all our implementation are so far. So which is way faster than building all of Athena each time and takes way less space. So that's what we are currently working on. So as an outlook, some of the ACTS tools have been implemented into Athena. So to facilitate future implementation, we will start soon to release this Athena nightly build with the latest ACTS version, which should help us to be more efficient in terms of implementing new tools. And finally, we are also continuing to compare the performances of the ACTS tools and algorithm with the equivalent in Athena. So that's all for me. Thank you.
Great, thanks a lot. Any questions?
Sorry, I don't know how to raise my hand, but I do.
That's okay, go ahead.
Okay, so earlier there was a slide discussing the ACTS material track use in material mapping.
Yes.
So there's code file ACTS write tracking geometry, or sorry, track writer, material track writer that seems to call on the material track header file. And this seems to be deprecated now. It is no longer.
No, if you're looking at the
code
online,
the current implementation.
The current version is not, the one that you can find in Athena right now is not the one used to make those plots. This is a private branch.
Okay.
So I mean, we still need to refactor it, clean it, and at some point we will probably push it.
Okay. Merci beaucoup.
Also, we still have not fully cleaned up. There's one item, the reintegration of all these writing modules, etc., which we had in our test framework now into a mono repository. So there's certainly some cleanup to be done.
Exactly.
Okay, I see Nick has his hand up. Nick, do you want to go ahead?
Yeah. So it's really nice to see all this progress that's being made. I was kind of wondering, now that we have all these kind of tools that you've shown here, is the main kind of work to be done on getting ACTS more integrated into Athena for Atlas use from the side of the actual, actually just using it in Athena, so putting this in rather than actually anything that the ACTS framework needs to provide in order for this to be usable? So, or is there things you also know that are kind of on the horizon that would be, you know, necessary for kind of starting to think about any proper full integration into Athena?
I'm trying to think. I mean, for sure, right now we still don't fully have this volume material, etc., that is fully implemented. So this is something that will come soon. But then I'm not sure there is much we will need from the ACTS side.
So I think actually what would be a major step from an adoption point of view from the Atlas perspective is that we basically need to support the interface that is exposed by the previous implementations of the propagation in Atlas. So basically this extrapolator interface that's used basically everywhere any part of the infrastructure needs to do particle extrapolation. And that is being worked on and off by basically only Noemi, and at this stage it's still in a very early sort of state. Yeah, so basically I think this is sort of one of the major things that needs to happen before we can look at trying to migrate parts that are not explicitly written for ACTS to the ACTS extrapolation.
And
okay,
then
thanks.
I will add one sentence, Nick, to illustrate what's really needed to be done to use it in an experiment. For the Kalman filter, of course, we have very intensive calibration tools in Atlas, calibrating the hit on track. Now, in the Kalman filter in ACTS, there is a slot for a calibrator that unpacks the source link to then give you back a calibrated object depending on your detector type. However, this code, the wrapping of the Atlas calibration needs to be Atlas code. This is not something we will drag into the ACTS core. So this glue code to basically wrap the existing calibrators and then use them in the Kalman filter is an example of code that needs to be written to enable the Kalman filter as a useful option.
Okay, thanks. In any case, it all seems encouragingly far progressed though, which is really nice.
Yeah, I definitely agree. It's really cool. So I see Tobias has his hand up. Tobias, you want to go ahead?
Yeah, that's right. So we also have in Panda a TRT type detector, so densely packed straw tubes. And my question is, how good are those already supported in ACTS? Because they have a bit different hit description than typically 2D planar detectors.
So we have the TRT, the straw detector description is fully available. What we would like not to copy over from how we dealt with that in Atlas is the fact that a detector that is sort of homogeneous at an approximation homogeneous in the material description is modeled as n layers of virtual material, which is what Corentin has been shown. Now we think the best description for this is leave the straw description of a straw detector as measurement straws, but decouple entirely the material question from that story. Then you don't have to do any navigation between layers rather than going from measurement to measurement. So you don't need to spend time on geometrical navigation, and leave the material to the step propagation. And this is what Corentin has been shown, and we will try to have, I think it's on the agenda on Wednesday, a discussion about TPC straw detectors everything which is more appropriately described such rather than with planar sensors.
Can I add something here? So one thing, maybe this was also sort of included in what the question was going for, is like from the EDM point of view, this should be fully supported. One thing that's crucially lacking from basically everything here is that we don't currently have any test setup, essentially, where we verify that this actually works. So from a design point of view, we were thinking about this, and this should be supported, but I'm not aware of any concrete implementation other than the geometry modeling of the TRT, which currently uses which currently models anything like this. So I think what we should really put somewhere on the to-do list and probably get to reasonably soon is actually adding, for instance, an example where the Kalman filter runs over straw measurements and verify that this actually works and produces correct results. Because right now we're not doing that, basically.
Yeah, I think that would be great to have some examples like that.
Well.
And Tobias, if there's more feedback from Panda, feel free to make a contribution to either Wednesday or Thursday. We intended these to be open, and if people want to add things,
sorry,
please do.
I did not say this in my introduction very clearly. There should be really also some sort of an open mic contribution possible, where you just say, we would like to have a support of this, and then we discuss how this fits into the plan, and if you can put person power onto that.
Yeah, sounds interesting.
Okay, any last questions? If not, we should move on.